we're going to solve problem 4-56. This is a problem with a distributed load across a beam supported at 2 points. We've got a beam supported on a roller at A and a pin joint at B. So the first thing we're going to do, our first step is going to be to create our free body diagram with all of our loads and equivalent forces. So to do that, we're going to first draw our beam. We have a beam that goes from point A to point B. And we have at a roller a vertical force. So we have the vertical force A. And this system is a coplanar parallel system. So all of our forces on loads on the beam are vertical loads. So we won't have any horizontal load at B, even though it's a pin joint. So we'll just label our vertical load or our vertical reaction force at B as force B. Next, we need to find the equivalent forces for this distributed load. To do that, we're going to divide the distributed load into 3 sections. We're going to look at this triangular section of distributed load. Then we're going to look at the rectangular section next to it, like this. And then we're going to look, lastly, at this triangular section here. So we'll replace each of these, we'll replace this distributed load with 3 point loads. To start, we'll do this triangle piece at the top. For the equivalent load of a triangle, a distributed load triangle, we want to take the magnitude of the load is equal to 1/2, we'll call this F3. F3 is equal to 1/2 of the base of that triangle times the height of that triangle. So that's going to be 6 meters wide, so 1/2 of 6 meters. And the height is 20 kilonewtons at the peak, but it's 15 kilonewtons per meter at the base. So the height is going to be 5 kilonewtons per meter. So if we multiply this out, we'll get 15 kilonewtons. So we have a force F3 of 15 kilonewtons. And if you look in your textbook, the example for distributed loads shows where to locate this point force. And that force is going to be 1/3 of the base from the high end, or 2/3 of the base distance from the low end, the tip of the triangle. So this distance will be 2 meters from the high side of the triangle, or 4 meters from the low side. So we can put this equivalent force of 15 kilonewtons 2 meters from this end of the triangle, or of the beam rather, excuse me. Next, we want to determine the equivalent load for the rectangular component. For a rectangle, the equivalent load is equal to the base of the rectangle times the height of the rectangle. So in this case, we've got 11 meters wide times 15 kilonewtons per meter. So that's going to give us 165 kilonewtons. And the location of that force is going to be halfway between the 2 points. So this will be 5.5 meters from point B and 5.5 meters from this point here. so 8.5 meters from point A. So we'll draw our equivalent force here of 165 kilonewtons. And we'll label this distance all the way back to point B as 5.5 meters. Next, we'll find the equivalent for the triangle on the left. And again, our equivalent load to a triangle is 1/2 of the base times the height of the triangle. So that's going to be 1/2 of 3 meters times 15 kilonewtons per meter. 1/2 of 45 is 22.5 kilonewtons. So we'll have a load of 22.5 kilonewtons. And that is going to be 2/3 of the way from point A, or 1/3 or 1 meter from this point here. So that's 11, that's 12 meters from point B. So now we have our free body diagram. We've labeled all of our distances and our forces, and we're ready to solve our equilibrium equations. So step 2 is set up and solve equilibrium equations. So we'll start with the sum of moments about point B. Counterclockwise is positive. That sum of moments has to be equal to 0. So our first moment is going to be the moment due to A. So we've got A times the distance to point B, perpendicular distance is 14 meters. And that's going to be a negative moment because it's a clockwise rotation about point B. And then we've got plus 22.5 kilonewtons times 12 meters plus 165 kilonewtons times 5.5 meters plus 15 kilonewtons times 2 meters equals 0. So we'll add A times 14 to both sides. We've got A equals, and if we calculate all of these, 22.5 times 12 plus 165 times 5.5 plus 15 times 2 is 1207.5. kilonewton meters. Divide that by 14 meters. And we get A is 86.25 kilonewtons. Now I'm going to move this out of the way. Now we can do our second equilibrium equation. We're going to do the sum of forces in the y direction is equal to 0. So we've got A is a positive force, and A we already know is 86.25. And we have minus 22.5, minus 165, minus 15 kilonewtons, plus B equals 0. B is going to be equal to, if we just calculate 86.25 minus 22.5 minus 165 minus 116. And add that to both sides, we get B equals 116.25. kilonewtons. And that's our solution to this problem. We've got B is 116.25 kilonewtons and A is 86.25 kilonewtons. So we found the two unknown reaction loads.